Okay, yeah. So my voice is almost shot, so I'm going to go until I can't talk anymore. Um, but I'd like to really thank you all for the time and attention you've given to this project Ted and I've been working on. Project, I guess. And it's been a real pleasure to give these talks. So I want to recall some of the setup that we had yesterday. We're sort of looking at a similar but different problem. So we had an algebra B, which was, and I went through it, I made it, so it's going to be the base change of an algebra B double prime. So I noticed in my notes that reduced norm 1 and prime all look the same. So now it's going to be B double prime. And at the real place, B is going to be product of two matrix algebras, and B double prime will be just single matrix algebra. And we're looking at these Shimura, ignore that for a second. We're looking at Shimura curves on a Shimura surface. So what are we doing? We're taking the reduced norm 1 elements of an algebra over a totally real field. And we're trying to understand that via the unit groups of subalgebras that give us our big algebra as a base change. And so what we're going to do is we're going to try to study these unit groups via some algebraic geometry. And so to do that, you usually need something smooth. So I'm going to pass to a torsion-free subgroup of the elements of reduced norm 1. And here's where you see why I changed to double primes, because the ones look like primes. So one thing you could do, it's an old fact due to Borel, that if you pass to the level 3 congruent subgroup, that's good enough. So you can keep this in a sort of number theoretic. You don't have to pass to a magic subgroup or something. And by our assumptions, so I made this assumption star that B ramifies at some finite place. And that tells us that this surface is compact. So it's going to be a smooth, compact, projective surface. And these base changes, and as Ted explained from a sort of easy Brauer group computation, if you get one, you get infinitely many. You might have none. But if you get one, you get infinitely many. And so what we get are these curves, possibly with some self-intersection. Now, they're smooth projective curves over here before we embed them in S. And they have G is at least 2. But they may have some accidental collisions inside of. And that actually ends up being a technical detail that we have to work pretty hard around. So question 1 is, can we understand these orders via the suborders that give us the base changes? And the somewhat equivalent question 2 is, can we understand these Shimura surfaces via the Shimura curves? And understand is a question to be determined. We're going to sort of talk in terms of the fundamental group, which is sort of most obviously related to the unit group. And I'd like to remark, just because it sort of fits best with the theme of this conference, we're sticking with these things acting on a product of upper half plane, but this also works for unitary Shimura varieties. And that's where this Albanese application, about which Ted spoke a bit yesterday, is sort of the most interesting. And so the Albanese variety is actually trivial when you have a product of upper half planes. And that's actually going to come up later, because I'm going to show that you can somehow do these things effectively. So that fact will reappear. Excuse me. So the theorem is there exists a finite collection of Shimura curves on this surface, such that, part 1, you take the divisor given by the inclusions, and that's a connected effective divisor. Part 2, for all open neighborhoods of this divisor, the map has finite index. Okay, and so you can really say that if you sort of collapse neighborhoods onto the divisor, that is the fundamental group of the divisor. So we're really saying the fundamental group of this divisor generates. Well, it might not generate, our group gamma, but at least up to finite index. So you get some finite index. And so, like I said, we're going to use some algebraic geometry to prove this, so-called weak Lefschetz theory. And this goes back to how Norrie resolved Zariski's conjecture in the late 70s, early 80s. And we'll see that, okay, so I'm telling you there's some number of curves that generates this surface. And the one thing I'm going to spend a bit of time explaining is how this is actually something you can compute. You can compute the number of curves you need on the nose. So, it comes from doing just a little bit of work. And that's where the place for this Albanese variety comes in. And I want to mention that so somehow there's an analogy here with two-dimensional class field theory where you sort of try to understand a two-dimensional scheme by sort of one-dimensional subschemes, how they glue together. And if you want to take an étal cover, somehow the subschemes are going to have to glue together to make that cover in a certain way. Sort of analogous ideas. Follow the gluing. So I'd like to mention just briefly. So these curves, these Shimura curves are negative. So their self-intersection is negative. Well, they might not be embedded. So if they are embedded, then they're negative. Right? There's this issue of the possible accidental self-intersections. So what's the idea of why these are negative? So essentially, we're taking these negative things and we're going to build something positive. So it's, in a sense, a little special. So you want the degree of the normal bundle. So you can conjugate this B double star. So, I mean, think about the easiest way to base change. It's just so that you take the tensor product, and now you're going to have the Galois group of K acting and fixing B double prime. And that corresponds to the diagonal map. And so you get the diagonal map from the hyperbolic plane into the product. And so that's the sort of hyperbolic plane on which this subgroup is acting to give you your curve. And so then you can just do a little computation. Well, what's the normal bundle? Well, it's sort of V minus V. Right? What's the normal bundle of the diagonal? You take V minus V. And so that action is isomorphic to the tangent bundle of the curve. So its degree is the Euler characteristic of the surface. And so I just wanted to throw that up there. It's a fun fact. And so the basic idea that we're going to want to apply here is the following. And so if you have, so it's all characteristic 0. If you have an étal cover, and if it supports a compact connected effective divisor with positive self-intersection, then your covering is finite. Okay? So basically, infinite covers don't have divisors, effective divisors with positive self-intersection. And that's the sort of fact that we're going to put together to prove this theorem. And I'll just for those who aren't so up on their intersection theory, there's the definition. And you can really just work in H2. That's the sort of thing that's going to come up a bit later. This intersection form only depends on H2. Yeah, sure. If you know how to do it. Okay, I'll continue while he goes after that one. So yeah. So what's the sort of punchline here? Is that if you have a connected effective divisor and you have an open neighborhood, now what am I going to do? I'm going to take the image of that fundamental group of that open neighborhood, and that's going to have finite index. So what does that mean? I'm getting a subgroup of a fundamental group, so I'm going to get some atol cover out of that. I'm saying that that atol cover has finite degree. And so you take the cover associated with this image, and then by sort of basic level 1 graduate algebraic topology, you lift, right? So D also lifts because it's contained in that neighborhood, and you keep the intersection the same, so it's positive. So, so you get a compact connected effective divisor of positive self-intersection, therefore by the theorem it's finite. Okay? So the goal is we're going to use these subalgebras to build a collection of Shimura curves with such that that divisor has positive self-intersection. That's going to be the game. Okay. A little high. Yeah. Is that okay? Sorry, I guess I wrote a little too small. Okay, so a little more algebraic geometry. So I'm going to sketch the proof of this theorem, go into a little bit more detail as to how you make it effective. And then I'm going to spend some time asking about some other problems that will hopefully pique the interests of some of the people here. Okay, so here's my divisor on a covering. And then I'll just throw the whole thing up. So you get the previous theorem by this sort of result, which says, okay, you've got this infinite atol cover, right? S was compact because it was a smooth projective thing. You take this cover, S hat is not compact, and you've got this connected compact divisor effective on it. And okay, so either the intersection is negative, or you have this sort of crazy condition about the square being having self-intersection 0. And you can read through it if you really care to, but the point is positive doesn't appear. Right? And so this theorem implies the other theorem, which said that you can't have, is it still up here? Yeah. So this theorem sort of goes into proving this. This is sort of a, I don't know, I found this sort of interesting. Sort of strong restriction on self-intersections of divisors that I didn't really know until now. So yeah, so this is the sort of machine that drives this theorem. And so how do you see this? You really turn it into some like algebra of quadratic forms, right? So the intersection pairing is a quadratic form on H2. And the divisor being connected tells you that when you restrict the intersection form to the subspace spanned by those irreducible components, you're getting a indecomposable quadratic form. What does that mean? When you write down the matrix, it doesn't have blocks, right? Because if I had blocks, then I would be able to divide my divisor into two pieces that don't intersect. Okay? And then this crazy condition 2 is a sort of geometric restatement of something due to Coxeter. And so he was looking at Coxeter groups which have an associated quadratic form, and he was proving theorems about those. He made this sort of observation that you can really get some nice geometric information. And he had a sort of similar conclusion, but when you put it in the algebraic geometry world, you get this great sort of conclusion that the C hat has to be irreducible. So yeah, that's basically the machine that goes into. I'm not going to state that. It's a little technical, and there are some notes that I hope to post. Sickness has really slowed me down, but that will contain sort of full proofs of these. I hope to post them soon. Okay, so where am I going here? So now, now I want to see why I can't have. So essentially, to prove this theorem, you need to prove that you can't have the positive self-intersection, right? That's still where we're going. So The point now is if you take one of these infinite covers, so again, I'm trying to prove that I can't have positive stuff on this infinite cover. So I take an ample line bundle on S, and I've got this étale covering with S hat non-compact. And now I'm on something non-compact, so I'm going to take, but fortunately I'm analytic, so I can do this, and I'm going to take L2 sections, L2 holomorphic sections of line bundles. So I'm going to start pulling back ample line bundles. And I'm going to get that this space is infinite dimensional. Okay. So, great. So the point is you can get infinitely many L2 sections. Now, the proof of this is very technical, and again, there's a proof in these notes that I'd like to post soon. But it's really, rather than sort of belaboring a proof right now, I'd just like to give you some intuition. So this is an infinite version of what you get out of Kodaira vanishing. So you get that the Euler characteristic of the cohomology of these line bundles is multiplicative in finite covers. So now when you're smooth projective, your compacts of L2 just mean every section is L2. So you can really just forget about the 2. And what I'm saying here is that right, the Euler characteristic by Kodaira vanishing is just the H0. So H0 is multiplicative. So it has to grow. So now you can, if you think about this infinite cover, this infinite étale cover as being a limit of finite étale covers, then you get that this degree is growing through the covers. So that's going to be infinite because it's going to be, the limit is d goes to infinity of d times that, or d times this, sorry. So yeah, when you get that S hat is actually a limit of finite étale covers, you can prove this pretty easily. Great. Okay, so this is sort of ingredient 1 of the proof, that these infinite covers can't have positive divisors. One is that you get these infinite dimensional spaces of sections. And then the second fact is that if you have an open neighborhood of a connected compact effective divisor, then the dimension of the sections is finite. So we're going to think about L as now being a pullback bundle to this cover. And I'm also not going to prove that. But in a sense, here's the basic idea. Positive things are ample. And ample things are supposed to see everything topologically, right? You think about sort of a generic hyperplane section, and this is it's really seeing all the topology and geometry of this. Now, if I'm in something infinite, and I have something compact, that's too small to be positive. It's too small to see all the geometry of this non-compact sort of quasi-projective thing. So that's really the key idea here, is that in an infinite cover, something compact is too small to be positive because it would force it to see all the geometry of the covering. And again, so to get this theorem, you apply the proposition lemma to the inverse image. So I had this positive thing downstairs, and now I know it lifts the S hat to something positive. So that covering has to be finite. Okay. So now let's get back to Schmorr curves. Now I'm going to get back to unit groups too. All this algebraic geometry is going somewhere. Okay, so like as Ted said, you look in the Brauer group and you see that if you get one of these curves on the Schmorr curves, you get infinitely many. Now, like I said before, you can work in H2, which is a nice finite dimensional vector space. So I can find a relation. Maybe I should have brackets around my C's. I can find a relation in H2 because I've got an infinite set inside a finite dimensional vector space. So I can find a relation. And you can, in fact, make all of these positive, but so that you get something effective by, well, if I had a negative thing on one side, I'd push it to the other side to make it positive. And so you can shift it around. So these M's and these N's are all positive. So you're getting an effective divisor, and where the irreducible components are distinct. And so that tells you that the self-intersection of this divisor has to be at least 0. Might be 0. So just having infinitely many of these things allows you to build a divisor that's positive. Well, it's maybe 0. So there's a little more work to do. And again, I'll get back to how you can do this effectively very soon, actually. So the point is, what would happen if I got excuse me. So if I got that the self-intersection of x was positive, I'd be happy. I'd have found this positive divisor made out of Shimura curves, and I'm off and running. But what if it were 0? Well, if it were 0, you can sort of use the commensurator, Heck operators, however you want to say it, to find another curve that intersects them. And basically, you know, these curves are just everywhere. You're just absolutely awash in them. So if life was being a little cruel to you, and you got that x had self-intersection 0, there are just so many other curves. You can pretty much pick one at random, but you can construct one explicitly too, using a little bit of algebra that intersects that non-trivially, and then you do the sort of standard trick where you take that plus a sufficiently high power of x, and then you get something positive. Okay. So again, the sort of magic of how many of these curves. It's like what you either have no curves or you're just so absolutely awash in them that it's amazing. So yeah. Now I want to slow down. I realize I'm going fast, but my voice is going faster. The number of curves is computable. Okay, so it's like you get this theorem. It's generated by some number of. You get this order, and you get this generated by some number of orders. You'd like to know how many. You'd like some sort of bound, and we can do that. So there's a formula due to Shimizu for the topological Euler characteristic of the product of upper half planes modulo the things of reduced norm 1. And it's, remember we had this totally real field K? So it's zeta of K evaluated at -1 divided by 2 times the product of the norms of the places at which B ramifies -1. Fantastic little formula. One of my favorite formulas. And so you sort of break down the Euler characteristic. And I'm throwing a little Hodge theory. I mean, if you just care about B1, you've got B1 and B2. But you get this by Hodge theory. You get this even finer. And the thing is, these are algebraic cycles, these curves. So I'm after this. These curves are nice algebraic cycles. So I'm after sort of computing this number, the H11. Okay. So great. I've got this sort of invariance of K and B telling me the topological Euler characteristic, which I break down. And then you have a theorem of Matsushima and Shimura, sort of a precursor to Matsushima's formula, which sort of opened up this whole world of using automorphic forms and cohomology. This sort of watershed paper of his. There was a precursor where they studied the specific case of product of upper half planes. And consequence is that the H10 part, in other words, the first Betti number, right, the rank of the first cohomology with constant coefficients is 0. And this immediately implies this fact that the Albanese variety is 0, right? Because the Albanese variety came from integrating one forms, and there are no one forms. So you can break it down now so that I can, I'm going to throw away, we know what our space is. So now we get that the topological Euler characteristic is just those Hodge numbers. And you also have the Euler characteristic, the holomorphic Euler characteristic. And then you've got Noether's formula. And for a product of upper half planes, you actually get the C1, you get this equality of Chern classes that C1 squared equals 2 times C2. And And it's one of those things like if you know Chern classes, you can do this computation. And if you don't know Chern classes, well, just believe me. I'm sorry to have to put you through this suffering. But the great thing is having that equality does something very nice to the previous equation, right? Because C2, okay, again, if you don't know this stuff, C2 is the Euler characteristic. So we get a formula in terms of the Euler characteristic, and we get this equality. Again, H1 0 by Matsushima Shimura is 0. I throw that away. And so I get this beautiful little equality out of it, which just cuts down to H11, which is an upper bound for the dimension of the space of algebraic cycles, is just that, 2 times that. Well, you plug this back into the formula for the Euler characteristic, and you get that the space of algebraic cycles is on the nose half the Euler characteristic. That's a fantastic little computation. And that's extremely helpful because now, you see, we need to build a relation in H2. We need to build a relation between these algebraic cycles. And to do that, well, I forgot the first time. So we were working with this gamma, which was a subgroup, because we had to go to torsion free. So the Euler characteristic will be the index of gamma in that. Now, if you took a nice, neat, congruent subgroup, then you can actually compute that index. It's just sizes of SL2 over finite fields. So you get this nice thing, and then you throw in one more so that you make sure you get a relation. So there's a formula for the number of curves you need. Bang. This is greater than the dimension of the subspace they span, so there must be a relation. So our machine just works. And fantastic. So again, just to restate what I just scratched, you get the gammas generated, well, up to finite index. So that's the thing we can't compute. No, actually you can. You can compute the index in terms of the intersection numbers. So you can tell how many curves, and you can actually get an upper bound for the index of the subgroup it generates using the intersection number. You have to compute that, but you can if you really want to. And so the question, I want to bring this back to the algebra. The question is, we did all this algebraic geometry, and we got this neighborhood of a union of Shimura curves generating basically the fundamental group. So it's saying that a sort of neighborhood of this nice collection of Shimura curves really sees all the geometry of this Shimura surface. Can we remove this neighborhood assumption? Because what happens if we remove the neighborhood assumption? Well, really, you can, what you want to say is what I have written here, is that inside of the unit group of this order of B, you can find unit groups of some collection of suborders where you want to be able to compute the number of suborders it's going to take, such that those are going to generate the whole unit group of the order. And that's a question that we haven't quite been able to answer, and it's because of this necessary neighborhood. And if you don't want to take a neighborhood, you should really be thinking about the formal completion. I can say that here. You all are scared of formal completions. So yeah, that's where we'd like to know that. And I think that's a nice sort of clean algebraic statement, saying that if you take an algebra that's a base change, at least, remember Ted made this comment yesterday, where you're never going to get the full unit group, because all of these unit groups are just going to have Q's, and so you're never going to get the multiplicative group sitting inside the unit group of this big order. But can you see the elements of reduced norm 1 of coming from some nice collection of reduced norm 1 elements of subalgebras for which your algebra is a base change? I think that's a nice question, and we'd really like to answer that, but we can't right now, so sorry. And so I'm going to change gears a little bit and try to pique your interest with some final questions. So one final question I would like to pose is all of this Lenstra stuff that came up in our first 2 lectures, can you do this over characteristic P? So can you understand, you can define a notion of height, you can make sense of Minkowski. I don't want to say that yet. So you can really sort of apply all the technology, and it seems to work. So I think it would be nice to see this for algebras over characteristic P. And this may be related to something called FPM. I think this was defined by Sayre. Certainly studied a lot by him. And so if you have a ring R, I'm pretty much going to take Z, but you take a ring R. So a group is FPM over R if there is a projective resolution, and so, of finally generated R modules. Okay? And so if you're FP1, so again, we find these finite generating sets. So if you're FP1 over Z, then you're finally, if you're finally generated. So exercise for those that are really bored. There's some real algebra for you. You're finally generated if and only if you're FP1. Okay. If you're FP2, that implies you're finitely presented. Oh wait, no, I did that. Oh, that goes the wrong way. If you're finitely presented, then you're FP2. There are examples that this is not an equivalence. But if you could show, yeah, so not FP2 implies not finitely presented, which is interesting, and not known in some cases. So I will sort of detail. So why would this be interesting for these algebras, these questions of FPM? And they should be sort of accessible, at least FP1 and 2 maybe, from the methods that we do in characteristic 0. So you have this theorem in Agao that SL2 FP adjoint T is not finitely generated. Of course, SL2 in characteristic 0 always is. That's great. But it's actually not finitely generated. Now, you can think about this as follows. What's a nice way to generate SL2? It's by elementary matrices. Now, if I try to generate SL2 by elementary matrices now over FP adjoint T or FQ adjoint T, then that's not finite generating set anymore, right? So that's a problem. And so, in fact, it's not finitely generated. And so the question, which I think, so this is understood for isotropic algebraic groups, if you know what that means. It's been long studied by Sayre and Hobbles and lots of people. Lots of recent work, actually. So it is the supremum of the length. I think this is totally wide open for S units of division algebras and characteristic B. As far as I can tell, it is absolutely wide open, except for the units themselves, which are FP infinity, which means you get projective resolutions of arbitrary length. What is the maximum length of projective resolution of the S unit group of division algebra? I don't think we have any idea. There's perhaps a conjecture you could make, and if you're really interested, I could tell you the conjecture, but it's a little technical. I think that's a really good question. And the other thing I'd like to ask is whether this stuff about Shimura surfaces and Shimura curves generalizes one to characteristic P. You can make sense of the neighborhood of a divisor via the formal completion. So this all makes sense, right? You don't have to take an analytic neighborhood. And in fact, really, the proofs in characteristic 0, you should really think about the formal completion anyway. So yeah, in characteristic B, do Shimura varieties really seen geometrically by their Shimura subvarieties in a precise way? And also, a couple more questions in characteristic 0 is if you look at UN1 Shimura varieties coming from Retian forms over CM fields, if you could prove a similar result about being generated by curves, you would get strong Albanese structure theorems that I think are unknown. Yeah, one thing that was proved in the U21 case by Murty and Ramakrishnan, they proved that they're all abelian varieties with complex multiplication if you're coming from a congruent subgroup, which is a just fantastic theorem. And basically, you could This is just absolutely classical problem, right? Which abelian varieties show up as Jacobians of curves? And you could now ask, well, okay, let's take a Shimura variety and let's look at its Albanese variety. Let's look at which principally polarized abelian varieties show up there. And these results would sort of be saying, well, you're not really getting that much more than you got from curves because you've got this collection of curves that just determines everything. So it's the quotient of a product of Jacobians of curves. Um, and so I think that would be actually pretty interesting. And similarly, there are these varieties of Kottwitz type, which are coming from instead division algebras of degree D. You take a Hermitian form in a division algebra. And these are very important in Harrison Taylor's work on Langlands, the cohomology of these varieties, though not the ordinary cohomology. But there are these other Shimura varieties of so-called mixed type, which come from matrices over division algebras, and their cohomology is just not understood at all. They're very inaccessible by like the trace formula and stuff like that. So if you could prove that those unitary Shimura varieties coming from matrices over division algebras were generated by the Kottwitz type subalgebras, you could apply a bunch of results of Kottwitz, Clauzel, Rogowski was the original. Rogowski was really the original one to prove these strong vanishing theorems. And then Clauzel generalized it from U21 to UN1. But basically, if you could say that these mixed type Shimura varieties were built out of the Kottwitz type ones, you could basically get more sort of strong cohomologically cohomological vanishing theorems. And my voice is gone, so I'm just going to stop.